Swayam Prabha. Digital India. Educated India.
So, we continue our discussion of time dependent oscillatory flows in a pipe. If you recall, we had considered the pressure gradient in the pipe to be an oscillatory function in time. Okay. It scales as cos of omega t, okay, over here. Rather than having a steady pressure gradient, we had considered an oscillatory pressure gradient. And the momentum balance equation, of course, was the same. This was for a fully developed flow. Assumption is that there is no variation in the velocity in the downstream direction, but the flow was not steady, it was oscillatory. Okay. Can a flow be fully developed and unsteady? Okay. In this particular case, the maximum velocity, okay, by which pressure is transmitted is at the speed of sound. Okay. The pressure transmission takes place through the fluid at the speed of sound. Okay. So, one can never have a fully developed flow because the pressure perturbations have to travel at the speed of sound. Okay. So long as the distance is small, the time scale for pressure transport across the pipe will be smaller than the much smaller than the time for the velocity, mean velocity. Okay. So, in that limit, we can consider the flow to be fully developed, but still unsteady. Okay. The assumption is that pressure is transmitted instantaneously, infinitely faster than the fluid velocity. In that case, we can consider the flow to be fully developed, that is, no variation in the streamwise direction, but still unsteady. Okay. Because any pressure differences that you put across the ends, they travel at the speed of sound, which is much faster than the fluid velocity. So, that is the assumption here, that the pressure perturbations propagate instantaneously. So, we had written down these equations for the flow in oscillatory flow in a pipe, and we had scaled them. In this particular case, we had chosen the viscous scales for the scaling of the equations, and we had got an equation of this kind, which contained a Reynolds number. That Reynolds number was based upon the frequency of the oscillations and the radius of the pipe and the kinematic viscosity. Okay. And we had actually got a analytical solution for this particular problem. In most cases, when we consider transport phenomena or fluid mechanics in complicated geometries, we will not get an analytical solution. Okay. In this particular case, we did get an analytical solution by first writing down the velocity as some function of the radius times e power I t. The real part of e power I t is the cos function. Therefore, the real part of the complex velocity field that I get by solving this equation should be the solution for the inhomogeneous term being the cos function. Now, I can separate out the dependence on time and the dependence on position here. Okay. I can separate out the dependence on position and the dependence on time, because if the equation is linear and the inhomogeneous forcing is of the form e power I t, then one would expect the solution also to have that same frequency. There may be a phase shift, but for a linear equation, the frequency has to be the same. So, on that basis, we had done this decomposition of the velocity into a part that depends only on radius times an oscillatory function in time. And once you do that, you get, for the part that depends only on the radius, that is v of r here, you get an equation which is an ordinary differential equation in the radius, which can be solved. Okay. And as I told you, that solution is a numerical solution. You can evaluate it, you can get numerical velocity profiles for that solution. but that solution in itself does not give you a physical understanding of what is going on in this flow. In order to do that, we considered limiting cases. The first limiting case was when the Reynolds number is small. I had given you the physical interpretation of that. The time for momentum diffusion across the pipe is much smaller than the time period of variation of the pressure function, okay, the time period for the oscillation of the pressure function. In that case, at any instant in time, the flow looks like a steady flow, but with an oscillatory pressure function. And with that, if I solve the equation, I just get the velocity profile to be the parabolic velocity profile, but with the pressure gradient given by the instantaneous pressure gradient at that instant in time. Okay. So, that is what turns out to be the solution for this in this case. Now, this is of course only when the Reynolds number is exactly 0. If the Reynolds number is small, but is non-zero, can we get an improved solution for the velocity profile? In other words, can we systematically improve this velocity profile to take into account the effects of inertia in the limit of low Reynolds number? So, back to my equation for V, I have I R e omega V, okay, is equal to, okay, plus, sorry, minus 1. Now, since R e omega is a small number, and we already have the solution when R e omega is 0, okay, what one can do is to write V as the sum, okay, V naught plus So, in the limit as R e omega goes to 0, the second term in this series will be much smaller than the first one. The third term will be much smaller than the second one, and so on. Okay. So, this expansion I can insert back into the equation for V. Okay. This expansion I can insert back into the equation for V. Okay. So, if I do that, what I get is I R e omega into V naught plus is equal to and I had a inhomogeneous term minus 1. Okay. So, that is the expansion that I get. Now, I can equalize terms which are of equal powers of R e omega on the left and the right side. Okay. I can equalize, I can write equations for terms that are of equal power of R e omega on the left and the right side. Okay. If I take R e omega tending to 0, okay, if I take R e omega going to 0, the power of R e omega power 0 terms which have 0th power in R e omega, okay, these are terms which are multiplied, not multiplied by any power of R e omega in this equation. Okay. In this particular case, on the left side I get 0, because even the left side, the first term itself is multiplied by R e omega. Okay. So, on the left side I get 0, on the right side I get 1 by R d by dr of R dV 0 by dr minus 1. Okay, so, that is all terms in this equation which are have the multiplied by the 0th power of r e omega. Okay. What about terms that are multiplied by the first power of r e omega? Okay. Power 1. Okay. On the left side I have I times V 0. Okay. On the right side the term that multiplies r e omega power 1 is this one, okay, is equal to Note that there is no inhomogeneous term because this term is only multiplied by r e omega power 0. Okay. This term is only multiplied by r e omega power 0. Okay. Then if I take terms that are multiplied by r e omega power 2, okay, I will get I V 1. Okay. This one is multiplied by the square of r e omega here, okay, on the left side. Okay. And on the right side I will get 1 by r d by dr of r d v 2. Okay. That is this one, okay, and so on. Okay. You can get higher and higher terms. Okay. We have to also get the boundary conditions at 0, 1, 2 order. In this particular case, at each order we require that, okay, V 0 has got to be equal to 0 at r star is equal to 1 and d V 0 by dr. Okay. The condition at r is equal to 0 is the symmetry boundary condition, that the velocity gradient has to go to 0. And at r is equal to 1 is the wall of the pipe, and at that location the velocity has to be 0 at all instants of time. Okay. Same thing applies for V 0, V 1, etc., okay, because I can expand the boundary conditions as well. Okay. So, the boundary condition is that V is equal to V 0 plus V 2 0 at r star is equal to 1 and partial V by partial r, which is okay. So, that is the second condition, and each of these boundary conditions you can take all terms of coefficients r e omega power 0, power 1, power 2 and so on, and get boundary conditions individually for each of those, and each of these will be exactly of the same form. Okay. V 1 is equal to 0 at r star is equal to 1 and partial V 1 by partial r star. Okay. And similarly V 2. So, those are the boundary conditions at each order, and you can sort of see a way in which we can solve this series of equations. For the first equation, it contains only V 0 and the inhomogeneous term. This was exactly the same equation that we had in the limit of 0 Reynolds number, which we had just analyzed. Okay, this is the same equation, the 0 Reynolds number equation that we had just analyzed. Therefore, we have a solution for that. Okay. we have a solution for the first equation. Okay. Okay. That solution is V 0 is equal to minus 1 by 4 1 minus r star square. Okay. Now, the equation at r e omega is order 1 here. Okay. This V 0 is appearing as an inhomogeneous term on the left hand side. Okay. The boundary conditions are homogeneous. Okay. The boundary conditions are just that the velocity is 0 at 1, the gradient is 0 at 0. Boundary conditions are homogeneous. Okay. This inhomogeneous term, the equation that we had already solved for, is appearing as an inhomogeneous term. Therefore, I can integrate it and get the solution. Okay. I can integrate it straight away and get the solution. Okay. Therefore, at r e omega power 1, the solution is of the form I into 3 minus 4 r square plus r power 4 by 64. Okay. And if you look at the next equation, I already have an equation for V 2 in which V 1 appears as an inhomogeneous term. However, V 1 is already evaluated here. Okay. So, I can just put in that inhomogeneous term and get the solution. Okay. Okay. The solution is a little bit complicated, but it is straightforward. Okay. You can just integrate out this equation with the boundary conditions to get the solution. Okay. Okay. So, I should negative sign here. Say 2304. Okay. So, as you can see, okay, you get a series of solutions of higher and higher order. Okay. That was obtained by doing this expansion for the velocity field. Okay. By expanding the velocity field in terms of this function r e omega. Okay. So, you can systematically improve, you can get the order r e correction, the order r e square correction, r e cubed correction, and so on. Okay. If you, as I said before, the order r e correction was just real. Okay. So, if I multiply this by e power I t and take the real part, I will just get cos t. That is exactly in phase with the pressure variation, as I had showed you in the last lecture. Okay. This function, the velocity is exactly in phase with the pressure variation. Okay. The first correction here is multiplied by I. Okay. So, if I take I times e power I t, okay, and take the real part of that, I will get something that is proportional to the sine function. Okay. And therefore, that is out of phase. So, the presence of inertia gives you a solution that is out of phase. Okay. So, it creates a phase difference between the pressure gradient and the velocity field. Because I have an I here, therefore, I will get u x star 1 will be equal to I into 3 minus 4 r square plus r power 4 divided by 64 e power I t. Okay. If I take the real part of that, okay, I will get minus sine t star into r square so that I am getting something that is exactly out of phase. The next higher order term is once again in phase, it is real. The next one will be out of phase, and so on. Okay. So, you can systematically correct this solution to get higher and higher order terms. Okay. These are called asymptotic expansions in the limit of Reynolds number going to 0. At Reynolds number is equal to 0, the flow is purely viscous. But if the Reynolds number is small but non-zero, you can bring in the effects of inertia on this flow by actually calculating the corrections to the velocity profile due to inertial effects. So, everything we have discussed so far is in the low Reynolds number limit. Okay. Let us go to the high Reynolds number limit. Okay. In this particular case, if you recall previously, we had scaled the velocity by the viscous scales. In this particular case, at high Reynolds number, since inertia is dominant compared to viscosity, we have to scale the velocity by the inertial scales. Let us go back to the original equation. Okay. Rho times dux by dt is equal to mu minus k cos of omega t. Okay. We had scaled r star is equal to r by r and t star is equal to omega t. Okay. With that, I had got rho omega times partial ux by partial t star is equal to mu by r square. Minus k cos t star. Okay. And I had divided this equation throughout by k, so that the inhomogeneous term became dimensionless. Okay. So, I had divided this equation throughout by k. Okay. And I have a k in the denominator here. And this k here disappears. Okay. Okay. Now, I have to scale the velocity by the inertial scales. Okay. So, I should define ux star is equal to rho omega ux by k. If I do that, on the left side I get partial ux star by partial t star will be equal to mu by k r square into k by rho omega into in order to not confuse with the viscous scalings that I had used previously, I will define this with a plus sign. Okay. Rather than a star, I will define it with a plus sign. Okay. So, if I do that, okay, okay, it is understood that u plus is scaled by inertial scales. Okay. And then my equation for u plus becomes partial ux plus by partial t star. Okay. You can easily see that the k cancels out here and I just get a factor of 1 over r e omega on the right side. Okay. minus cos theta star. Okay. As before, instead of using cos as the inhomogeneous term, I would prefer to use e power I t. Okay. If I use e power I t, the only difference is that I will get a complex solution for the velocity. When I take the real part of that, I will get the actual physical velocity profile. Okay. So, rather than using cos, I will use e power I t star. Okay. And then I express u x plus is equal to some w of r star, some other function e power I t star, okay, and insert that into the balance equation. I will get I, okay, times w times e power I t star, because if I take the derivative of this e power I t with respect to time, I just get a factor of I coming out. Okay. And w is only a function of r. So, when I take the derivative of that, okay, it comes out of the differentiation. Okay. This becomes 1 by r e omega into 1 by r d by dr of r dw by dr e power I t minus e power I t. And I can divide throughout by e power I t to get an equation which is an equation for w alone. Okay. That equation for w will be I times w is equal to minus 1. Okay, so, that is the final equation for w, and w has to satisfy the boundary conditions, okay, at r is equal to 0, partial u x plus by partial r is equal to 0, okay, the symmetry condition because of the cylindrical coordinate system, and that implies that partial w by partial r is equal to 0. Okay. And at r star is equal to 1, u x plus has to be equal to 0, okay, because you have a no slip condition at the wall at r is equal to 1, and that implies that w is equal to 0. Okay. Good. So, the only difference was that I have a 1 over R e in the viscous term instead of an R e in the inertial term. In the limit of R e going to 0, the inertial term goes to 0 because it is multiplied by R e. In the limit of R e becoming large, the viscous term can be neglected because it is multiplied by 1 over R e. Okay. And if I neglect the viscous term, I just get an equation I w is equal to minus 1, okay, which implies that w is equal to minus 1 over I, which is just equal to I itself. Okay. So, that is the solution for w. The solution for u x plus will be equal to w e power I t is equal to I times e power I t. Okay. And the real part of that will be u x plus, okay, the real part of u x plus will be the real part of I e power I t, which is just equal to minus sine of t star. Okay. That is the solution that we have, and we have to now enforce the boundary conditions. Boundary condition at r is equal to 0, dw by dr is equal to 0. This equation does satisfy that boundary condition. The second boundary condition, at r is equal to 1, w has to be equal to 0. Does this equation satisfy that boundary condition? We cannot satisfy the boundary condition because we did not have any constants of integration in this equation. Why is that? In the limit of high Reynolds number, when we had neglected the viscous terms, we are not able to satisfy the boundary condition. Think about it. We will continue this in the next lecture. Why is it that we are not able to satisfy the boundary condition in this case? I will give you the physical reason as we go along in the next lecture. We will see you then.